Good morning. Today we are going to talk about statistical power. This is a cartoon figure showing what statistical power is about. And this time, apart from the null hypothesis, we are also going to consider an alternative hypothesis where there is an effect. You can imagine this as having not one, but two populations of mice with different mean body mass. And the difference between these two populations is represented by an effect size. We take a sample from one population, a sample from the other population, perform a statistical test, for example, a t-test, and then we find and we decide whether the result is statistically significant or not. Now, the question for statistical power is as follows. How does our ability to call a change significant depend on the effect size and on the sample size? First, we have to understand a little bit better what effect size is because it has a very specific definition in statistics. Effect size describes the alternative hypothesis. If you consider this the null hypothesis in red, the blue line would represent an alternative hypothesis with a different mean. And this is the effect size, and we ask how large is it? Effect size is defined differently for each statistical test. For the t-test, when you measure the difference between the means in two different samples, the effect size is often defined as the coens d, which is given by this formula. It is the difference between means from the two samples divided by a standard deviation. And in this particular case, the standard deviation is given by this formula. It's exactly the same as we used in the t-test where variances were equal. This is a common or pooled standard deviation. The figure on the left shows two samples. The mean is represented by the horizontal bar, and the effect size, the coens effect size, is 1.1. The effect size has two crucial properties. First of all, it depends on the standard deviation. In these figures, there are three examples of data, two data sets, where the difference between the means is exactly 20 grams. This is the body mass of a mouse. There are two samples of, let's say, English and Scottish mice, and the mean of English mice is 20 and the mean of Scottish mice is 40 in every case. However, the standard deviation in each sample is different. We start with a very large spread of data and end up with data which is very concentrated around the mean. As you can see, the coens d, the effect size, is smallest here, 1.4, and then goes up 5.4 and eventually 26 in this case. The effect size depends on standard deviation. And the second crucial property is that effect size does not depend on the sample size. These are three samples, three examples of data with exactly the same effect size. Effect size is 0.8. If you perform a t-test on these samples, you will get three different p-values. As the sample size increases from 5 to 20 to 50, the power of the experiment also increases, and you are capable of detecting smaller effect sizes. Here on the left, the test is not powerful enough to detect the effect size of 0.8. It returns a p-value of 0.2, which is above our standard limit of 5%. On the right-hand side here, there is enough data, the sample size is large, p-value is very small, and we have plenty of power in this experiment to detect the effect size of 0.8. We can use several statistics to compare two samples. The simplest one would be simply the difference between the mean. It describes the difference, but it doesn't tell you anything about statistics. It doesn't tell you anything about spread of data. It's a very simple thing, but sometimes useful. Often we use a ratio. Sometimes it is used as a logarithm of ratio, the so-called log ratio, which is very useful in some applications. Cohen's d is defined as the difference between the means divided by the standard deviation. This is our effect size it takes spread in data into account. And finally, the t-statistic is directly related to statistical significance. It takes a spread of data and sample size into account. This is the difference. This is Cohen's d. We divide by standard deviation. In t-statistic, we divide by standard error. Effect size describes the alternative hypothesis. And effect size is not related to statistical significance. It's a different thing. Effect size will tell you how different the two samples are, while the t-test will tell you if this observed difference is statistically significant. Effect size in ANOVA is defined in a little bit more complicated way. We consider this data set of 4 nations of mice. The sample size, for simplicity, is equal in each sample. Test statistic, if you remember from ANOVA, the test statistic, capital F, is the ratio of variances, the between groups variance and within groups variance. And when there is no effect, this F is close to 1. We can say that the null hypothesis in ANOVA is that these two variances are equal. Now we can make an alternative hypothesis, I will call it H1, where the between variance is the within variance plus some excess variance, we'll call it additional variance or added variance, MSA. For normalization reasons, is multiplied by the sample size. And then Cohen's F is the ratio of this additional excess variance to the within variance. Where there is no effect, this would be 0. And this is how you link the F statistic with Cohen's F. F squared is F minus 1 over N. Here you can see 2 examples of ANOVA where the effect size F is exactly the same. This is the problem with ANOVA, that ANOVA tells you that something is different, but you don't know what. On the left, one group, Northern Irish mice, they have, well, quite larger mass than other groups. On the right, there are 2 groups higher, 2 groups lower, and they both produce exactly the same effect size. This is a summary of effect sizes we are going to use. When you compare 2 data sets and you use a t-test, then the corresponding effect size is d and is given by this formula. This is how it relates to the test statistic t. When you have more groups of data, then you use ANOVA, and related effect size is Cohen's F. And this is how it relates to the test statistic. The 2 additional things I'm going to briefly mention. When you do a chi-square test, then you can use Cohen's W, which is the square root of chi-square statistic divided by the total number of points. For correlation, the effect size is simply Pearson's correlation coefficient. We are going to use all these effect sizes now. Now we know what the statistical significance is. We've learned it already. And now we also know what the effect size is. So let's get going with statistical power. You have seen this slide many times before. This is how statistical testing goes on. You start with a certain model, the null hypothesis that there is no effect, collect your data, perform a test, find a p-value. If p-value is less than a significance limit assumed before, then you reject H0 at your own risk and you claim that effect is real. When p is greater than alpha, you accept H0. Well, you probably shout now, this is a heresy. I know I've been, through all these lectures, I've been banging on about how you should never, ever accept the null hypothesis. So what's going on? Of course, I was right. When you perform a statistical test, just one statistical test, you should never, ever accept the null hypothesis. But now we are going to see what happens if you do. We need this to understand statistical power. This table is central to today's lecture, and there is lots of things going on here, so I'm going to take it slowly. Columns in this table represent a hidden, unknown reality. Either that there is no effect, that means the null hypothesis is true, or there is an effect and the null hypothesis is false. The rows in the table represent our decision. Based on the result of the statistical test, we either reject the null hypothesis or accept it. When we reject the null hypothesis, we say, aha, we see an effect and we see strong evidence against the null hypothesis. This is called a positive. A positive result is when you detect an effect. However, if you do not reject the null hypothesis, and in this particular case you accept it, then it is called a negative. You don't find an effect. Inside the table, there are consequences of our decisions. If the null hypothesis is true, that means there is no effect, and we reject it, then we commit type 1 error. This is what it's called. It's easier to understand when you call it false positive. There is no effect, but we say, hello, yes, we detected an effect. So our positive is false. And this is governed by the statistical limit alpha. So the probability of this type 1 error is alpha, and we set it before we do the experiment. If the null hypothesis is true, that means still there is no effect, and we accept it, which means there is no effect, and we say, no, there is no effect, we did not find anything. This is a true negative. Now, what happens if the null hypothesis is actually false? That means there is real effect in your data and you're trying to detect it. If you reject the null hypothesis and say, it's positive, we see an effect, then this is a correct decision. This is a true positive. There is positive in data and you say it's positive. When you accept the null hypothesis, in this case, you commit a type 2 error, which is governed by this probability beta. I will explain it in a second. This is a false negative. The false negative is when there is a real effect in data somewhere in real life, but you are unable to detect it. You miss something. Type 1 error, type 2 error, this is a commonly used terminology, but I'm not going to come back to this. I will simply call these things false positives and false negatives because it's much easier to remember what they are if you describe them this way. Let us do yet another Gedanken experiment, a simulated experiment. We draw 100,000 pairs of samples, let's call them X and Y, of size 5. And for each pair of samples, we find a t-statistic. If you remember, it's defined as the difference between the means and divided by the standard error. This is what is used to find a p-value. And we build the sampling distribution of t. First, let's do it assuming that there is no effect and the null hypothesis is true. That means we draw both samples from the population with exactly the same mean. And you know what happens here? We did this for the t-test. We did a similar thing for the confidence interval of the mean. You will get a distribution of a statistic t, which is students' t distribution. However, if there is an effect, if there is a real effect, so we draw one sample from a population with 20 grams and the other sample from a population of mean 30 grams, we will get a distribution which looks different. First of all, it's shifted to the right away from 0, and it's also asymmetric. It turns out this is also a T distribution, but with the so-called non-centrality parameter not equal 0. Okay, we have these two distributions under the H naught and under the alternative hypothesis. Now things get a little bit complicated. First, consider a case where the null hypothesis is true and there is no effect. Based on the result of the statistical test, you will get a t-statistic, and depending on the value of this t-statistic, you can either reject the null hypothesis or accept it. The rejection region is in the tails of this distribution and is marked as a dark shaded region under this curve. It contains probability alpha. There is half alpha on the right and half alpha on the left. If alpha is 5%, you have 2.5% on each side. The region in the middle, which is called the acceptance region, contains probability 1 minus alpha. When the null hypothesis is true, like in this case, and we get a t-statistic in a rejection area, we reject the null hypothesis, we get a false positive. The null hypothesis is true, but we reject it. So false positives are here on the right and on the left, while in the middle there are true negatives. This is when we accept the null hypothesis and there is no effect and null hypothesis is true. If the alternative hypothesis is true, we get a different picture. The acceptance region, which is marked here with a dark shaded area, has a probability beta. This probability beta depends on the effect size. You can imagine this entire probability distribution being shifted to the right and left, and then the probability in this region, beta, would be different depending where the distribution is. This is a false negative region. We accept the null hypothesis, but the null hypothesis is false. There is an alternative hypothesis. There is an effect, but we say here there is no effect. So if our t-value is here, this is a false negative, and here there is a true positive. And the probability of the true positive is 1 minus beta. This is the power. It's the probability that we correctly reject H naught. The alternative hypothesis is true, and we reject the null hypothesis. This is the true positive. Statistical power is the probability of correctly rejecting the null hypothesis. And I think a much easier way of remembering this is to say that it is the probability of detecting an effect which is really there. If you want to detect an effect in your experiment, you need power. So far, we have used just one alternative hypothesis, very arbitrary one with an arbitrary effect size. Now we can try to repeat these calculations for several different effect sizes. The mean of the alternative distribution is 22, 24, 6, 8, and 30 grams here. So the effect size is getting bigger and bigger as you go from top to the bottom. In the top plot, the Cohen's d is 0.4. In the bottom plot, Cohen's d is 2.0. And from this, you can find power, 1 minus beta. This is the dark shaded area. And power is about 8% in the top plot, and then goes up and reaches about almost 80% in the bottom plot. Using this, you can create a power curve. This is the power as a function of the effect size. This is what it looks like for the sample size of 5. When the effect size is very small, like in the case at the top, the power is also very small. And then when you increase effect size either in the positive or negative direction, t-test is symmetric, it doesn't matter. Your power goes up, and eventually when effect size is large enough, power reaches 1. You have 100% chance of detecting the effect. Once again, power is the probability of detecting an effect when the effect is real. This was done for just one sample size of 5, and this figure shows a set of power curves for a few sample sizes. The larger the sample size, the higher the power for a given effect size. If you look at the effect size of 1 here, for example, then power for a sample size of 2 would be maybe 10%. For 3, somewhere around 20, and it goes up. And eventually it reaches 80% for a sample size of 10 or so. Just like the 5% limit on p-value is very commonly used in biological sciences, the power of 80% seems to be the norm. People consider this, if you achieve power of 80%, this is enough. Once again, the statistical power tells you how good your experiment is at detecting a given effect size. And to find statistical power, you need both sample size and the effect size. However, we usually go the other way around. We want to know the minimum sample size to achieve a given power. For example, we want to achieve power of 80%. What sample size do we need to find a given effect size? You can do this in R using a library PWR. If you load this library, you can then use this function, pwr.t.test. It works in a way that you provide with 3 out of 4 values plus an alternative. In this particular case, you provide the effect size of 1, the power of 0.8, and you say what type of test it is, whether it's 1 sample or 2 sample, and an alternative. And you also should provide the significance level, which I missed here, but it's by default is 5%. And then this function will collect information and find the missing information. In this particular is the sample size. So you provide it with the effect size, significance level, and the power, and it finds that you need the sample size of at least about 17 to achieve power of 80% at the effect size of 1. If you request higher power, for example, 95%, like in this case, this is exactly the same. I only replaced 0.8 with 0.95. That power calculation will tell you that you need a sample size of about 27 or more. I will come back to this later when I show you a worked example, how to do this in real data. Now I'm going to talk about statistical power in ANOVA. We apply the same approach as in t-test. First, we assume that the null hypothesis is true and there is no effect. And under these conditions, we create a simulation and we create a null distribution of the statistic F. This is the statistic in ANOVA. This is our null distribution. Then we consider an alternative hypothesis. The null hypothesis is where all means of all 4 samples are equal, let's say 20 grams. Here I pick one particular completely arbitrary alternative hypothesis where the samples 1 and 2 have the mean of 20 grams and samples 3 or 4 come from a population of 25 grams. You build a distribution of the F statistic, and just like we did for t-test, we cut off this area acceptance region. This is our beta. This is 1 minus beta. In this particular case, beta is 0.2. And then you can continue with this for different effect sizes, calculate power depending on the effect size and on the sample size. Just like as we did for t-test, you can create a set of power curves where there is effect size, it's positive only in ANOVA, and there are several curves for different sample sizes. Again, you see the same effect. To achieve power of, let's say, 80%, and to detect a given effect size, you find the minimum sample size. The smaller effect size you want to detect, the larger sample you need. This is how you do this in R. You use the same library. You use the function pwr.anova.test, and you provide it with the number of groups, which is 4, effect size, which is Cohen's effect size, which is 0.4 in this particular case, significance level, and the requested power. And this will tell you you will need sample size of at least 18 to achieve this sort of power. I will only mention statistical power for chi-square test and significance of correlation. I will skip all the mathematical details, just show you how you do this in R. You use the same library, PWR. You prepare a table, for example, this one. This is an example we talked about patients and drugs. There is a contingency table. You perform a chi-square test just to get a chi-square test statistic, which is statistic chi-square, and then find the effect size. This is what I showed you earlier in this table. This is the square root of chi-square divided by the total number of data points. This is sum of all counts, which is 180. And when you find it, you can do power chi-square test, providing the effect size, number of degrees of freedom, and requested power. And it will tell you that if you want to detect this effect size as in this table, you need at least 250 or so data points. We have 180. So this particular experiment is slightly underpowered. Very similar and a bit easier for correlation test. You do power test, power.r test, and you simply provide with a correlation coefficient and the requested power, and essentially that's it. The top example shows a sample size of about 13, which is required to detect a correlation of 0.7. If you want to detect a smaller correlation like 0.5, you would need a larger sample size. This all is a lot of knowledge to absorb in a very short time, and is probably a bit confusing. So let us go through an example which is based on real data, which we did a couple of years ago. Based on the pilot experiment, we wanted to do some power analysis. The pilot experiment was about tumor growth in mice. There was a wild type and 4 different knockouts, and we observed tumor growth and measured the volume of this tumor after 10 days. And this figure shows result from the experiment. Based on this pilot experiment, we asked ourselves 2 questions. First of all, how many replicates do we need to detect a twofold change between conditions? And this twofold change is a completely arbitrary number. We decided, well, if it changes by factor 2, it's probably something real. You notice that we start doing a bit hand-wavy things here. We assume some numbers. Unfortunately, power analysis is like this. It's a little bit of an art, a bit of a black art, actually, where you assume some things out of thin air, actually. And the second question was, how many replicates do we need to detect the observed effect size in ANOVA? So we take all these groups, we calculate what effect size is here, and we ask how many data points do we need to actually detect the effect size like this? First, let us answer the first question. We want to detect a twofold change between wild type and a knockout. And to answer this question, or to do any power test for t-test, you need to know, or at least estimate, standard deviation. And we estimate standard deviation from our data. The plot on the right shows the standard deviation for each group plus minus standard error of the standard deviation, which is given by this formula. And it shows you how spread this standard deviation is. And based on this figure, we decided to consider 2 cases. An optimistic case where standard deviation is rather lower, and we decided to take standard deviation of 75, and a pessimistic case where standard deviation is larger, and we take 160. These 2 scenarios of 75 and 160 are shown in this figure. First, we need to find Cohen's d. The difference between the means is 200. This is our twofold change. We decided it will be change between 200 and 400. This is a change of about 200. Again, it's all very kind of vague and hand-wavy. So if a delta M is 200, and we divided it by the standard deviation, the two cases, the optimistic and pessimistic case, and we get a Cohen's d, the effect size of 2.7 and 1.25, and they are shown here as vertical dotted lines. This is the optimistic case, and to achieve power of 0.8, you need, well, at least 3, maybe 4 replicas. But in the pessimistic case, you see, to get this power, you will need more than 10 replicas. You can find these numbers exactly in R. You perform a power.t.test for effect size of 2.7. This is our optimistic case. And that gives you a required sample size of just over 3, let's say 4. But in the pessimistic case, the required sample is 11 or so. Now, the second question was, how many replicas do we need to detect the observed effect size in ANOVA? And there it is. ANOVA gave us F value, the F statistic of 2.31. And from this, we can find Cohen's effect size. Remember, the F statistic, the capital F, this is not effect size. The effect size is a small f, which is given by this formula, and it's 0.47. And for this effect size, we see that in order to achieve power of 80%, we need about 10 or 11 samples or so. This is the second case. This is how many replicas we need for ANOVA. You can follow these calculations by downloading data from this URL. First, you need to perform ANOVA. So as I told you before, you build a model of volume versus group. You perform ANOVA, and then in this rather nasty way, you need to extract statistic F from this object. You can simply perform ANOVA. It will show you things on screen. You can copy and paste if you just do this in RStudio in an interactive way. This is our test statistic, and small f is the effect size given by the formula from the previous screen. And then you can do power ANOVA test for 5 groups of data for the sample size of 6. This is what we have in this particular experiment, and for effect size f. This will answer the question, what is the power of our actual pilot experiment? And after giving all these data, you will find that power is just over 40%. This is a seriously underpowered experiment. So if you want to perform it correctly, we need power of at least 0.8, maybe even more. And now, if instead of the sample size n of 6, you provide it with power of 0.8, it will find the sample size for you. And it's 11.9, it's almost 12. These are conclusions from this worked example. We want to achieve a power of 80% of 0.8. To detect a twofold change between wild type and A knockout, in a pessimistic case, you need at least 11 mice in each group. And the second question, to detect a change across all groups in ANOVA, we need at least 12 mice in each group. So based on these two predictions, we recommend an experiment with at least 12 mice in each group. I say at least because you have to account for possible failures, for possible failed experiments where you need to reject some of the results. This is everything for today. Thank you.